You know that smartphone in your pocket or the AI that seems to be shaping our future? It can all feel like straight up magic. But here's the thing, it's not. It's actually something way more interesting. Today, we're going to pull back the curtain and demystify that magic, revealing the simple yet powerful ideas that make our entire digital world work. All right, let's just dive right in. Think about the tech we use every single day. We can literally talk to our devices and they talk back. They understand what we want, play our favorite song, or find an answer to a question in just a split second. And then you've got smart cars, right? These things are using this whole web of sensors and incredibly powerful computers to see the world around them and, navigate through traffic safely, all without us ever touching the wheel. And it goes even further than that. We're talking about entire virtual worlds, the metaverse, you name it. Digital experiences so immersive they can feel just as real as the room you're in right now. It's pretty wild. So you look at all this, and it just seems impossibly complicated, right? So how in the world does any of it actually work? Well, we're going to start from the very beginning, building it up layer by layer to see what's really going on under the hood. To really get a handle on today's tech, you kind of have to know its origin story. So let's do a super quick, lightning-fast tour of the history of computing to see how we got here. Okay, so if you look at this whole timeline, a really clear pattern starts to show up. We started with stuff that was purely mechanical, like the abacus. Then we jumped to these giant room-sized machines with punch cards and these big, hot vacuum tubes. The real game changer? The transistor. That's what finally made computers smaller and faster. And then, bam, the microprocessor. That put an entire computer brain onto one tiny little chip. Every single one of these steps was driven by the same two goals: make it smaller and make it faster. So what's so incredible is that every single modern computer, I don't care if it's a massive supercomputer or the tiny watch on your wrist, is built from the same two fundamental parts working together. Just two parts. Okay, first up, you've got the hardware. This is all the physical stuff. You can touch it, you can hold it, the screen, the keyboard, all those little chips and circuits inside the case. This is the body of the machine. And then you've got the software. You can't touch this. These are the instructions, the programs, the apps. It's the intelligence, the mind of the machine that tells all that physical hardware what to do. Now, right at the heart of all that hardware is the CPU, the central processing unit. This is the brain, for sure. And it has two main jobs. The control unit is like a traffic cop, directing where all the data needs to go. And then there's the arithmetic logic unit, or ALU. You can just think of that as the master calculator. It does all the math and makes all the logical decisions. This brings us to something that trips a lot of people up: the difference between memory and storage. Think of it like this. Memory, or RAM, that's your desk. It's a temporary, super fast workspace for whatever you're doing right now. But when you turn the power off, poof, the desk is cleared. Storage, on the other hand, is the permanent filing cabinet. It holds all your apps and files safely, even when the computer's off. So you have all this incredible hardware, but how does it all communicate? It needs a language. And what's wild is that this language, at its very core, is shockingly simple. It's called binary. And here's the mind-blowing part. Every single piece of information, every word you type, every pixel in a photo, every note in a song gets broken down into a long string of just two numbers, ones and zeros. That's it. 1 represents an electrical switch that's on, and 0 represents one that's off. Just let that sink in for a second. Your favorite video game, a complex scientific simulation, even an AI generating art, it's all at its most basic level, just billions of tiny switches flipping on and off at unbelievable speeds. So, a single computer is powerful, absolutely. But the real revolution, the thing that changed everything, started when we figured out how to make them talk to each other. A computer network is just a collection of connected devices that can share info. But think about the internet today. With billions of devices connected, how does a message from your phone find its way to a server halfway across the world without getting completely lost in the chaos? The answer is a set of rules, or protocols, that work in layers. Kind of like a digital postal service. It's brilliant. First, your message is written. Then, it gets broken up into tiny digital packets. Each one of those packets gets a specific address, and then they're all sent out as electrical or light signals. And then they get perfectly reassembled at the other end. It's an incredibly elegant system for managing chaos. Okay, so let's zoom back out. Now that we have the fundamental building blocks, we have hardware, we have software, and we have networks. We can really see how they all come together to create the advanced tech of today and, well, whatever's coming tomorrow. It's this powerful combination that makes it all possible. You need that incredibly fast hardware to run the calculations, you need intelligent software to make sense of it all, and you need those global networks to connect everything and everyone together. And this is exactly how artificial intelligence works. It's not magic, it's just using these core principles on a massive scale. AI uses that powerful hardware and smart software to process huge amounts of networked data, which lets it understand speech, recognize images, and even perform complex physical tasks. And that same combination is what makes virtual reality possible. When you have powerful local hardware rendering graphics, intelligent software tracking your movement, and high-speed networks connecting you to others, well, you can create experiences so immersive they actually trick our senses into believing we're somewhere else entirely. So here's the big takeaway. We successfully taught machines to compute and to connect. Now we are in the process of teaching them how to learn and even create. We've laid this entire foundation, piece by piece, from an ancient abacus to a modern algorithm. The only real question left is, what are we going to build next?